Good afternoon. So today we are going to look at the I2C peripheral of the ML51. This is a rather interesting peripheral. So I have it here on the TRM. So the I2C basically consists of two lines, the SDA and the SCL, where SCL is the clock and SDA is the data line. So this is basically a bidirectional communication port. So, like I said, there are two lines, SCL and SDA. Now, both of these have to be open drain. So, both of these have to be open drain. And a low level on an SDA line is generated when one or more devices are outputting a 0, and a high level on an SDA line is generated when all the devices like this one and this one, all the devices are outputting a high on the SDA line because this is open drain, right? So that means that when you write 1 to the port, it is basically held high just because of this resistor, and when you write low, then it is pulled down by the internal FET. Okay, so we're not going to get too much into the detail of the I2C bus. That's a topic for another day. So here we just go through the briefs. We have the start condition and a stop condition in the I2C. This is the start condition and this is the stop condition. So the start condition occurs when the SCL line is high and there is a high to low transition on the SDA line. Similarly, a stop condition occurs when the SCL line is high, but a low to high transition occurs on the SDA line. So so much so for the high and low. Then the ML51 supports 7-bit addressing for the I2C bus. Okay, so the read-write bit, here we have the read and the write bit. The read-write bit determines whether the transfer is a read or write. And when a master writes data to a slave, and when a master writes data to a slave, like in this example here, and the ACK that we see here, the acknowledgement bit, that's this one, is generated by the slave. And when the master is reading data from the slave, when the master reads data from the slave, like in this example here, the master is reading the data. Here the read bit is 1, so master is reading the data from the slave device. At this point, the ACK bits or the NAC bits are generated by the, you got it, master, are generated by the master. Once again, if it's a write operation, the ACK or the NAC bits are generated by the, you got it, the slave. And when you have a read operation, the ACK and the NAC bits are generated by the master. Okay, so with that in mind, we shall proceed further and talk a little more about the arbitration. So what is an arbitration? What is an arbitration? Okay, so an arbitration basically means that a master, say it's a multi-master system, and there are multiple masters on the I2C bus. Now, if two masters start communicating simultaneously, then what will happen? Who will gain access to the bus? So that process is resolved via the arbitration. So what the arbitration says is that, let's say there are two masters and they have their start bits. Here a start condition is generated by both the masters. This is master 1 and this is master 2, and we are generating a start condition. The clock line is high, so a start condition is generated. Now the start condition completes and both the masters proceed further. Both the masters send a low bit out. Now the master which then releases its bus, the master which then releases the SDA. So this master 1 is trying to output a 1, but master 2 continues with 0. And when the clock goes high, at that point, if the master which releases his bus, that means makes it 1, loses arbitration. So any master which releases his bus then loses arbitration. So here we see that the dominant is 0, the 0 is dominant or the low is dominant. So any master which releases its bus loses its arbitration. So how does that happen? Every master is also reading what it is putting out on the bus. So if it puts out a 0 and it gets a 0, it says okay, no problem. Now in this case the master is putting out a 1 but because 0 is dominant, it continues to see, it will continue to see 0. And when it says, it knows that it has put out a 1 but it is receiving a 0. At that point it knows that it has lost arbitration. Now at this point, master 1 will release the bus. Master 1 will release the bus and master 2 will continue to operate as the new master. Okay, so so much so for that. Now the thing with the ML51 implementation is that it's a very tricky implementation, and it's a very good implementation at that, because it has inherent protections against I2C bus latchups. So this is more like an action and a reaction scheme. So there is an action and then there is a reaction. So what is the action? By the way, I just use a small iPad as a prompter. I have this iPad mini which I make all my notes, and then I just try to go through them. So if you see that I'm turning here and there, basically I'm just trying to get a prompt from the iPad. Okay. So here we see that there is a status register, and then there is a control register, and then there are three registers basically: a status, a control, and a data register. Okay, so how does the ML51 scheme work? Basically it's an action reaction scheme. That's how I would put it. That means that for every action you have to look at what reaction that action has caused. Okay, so what does that mean? Now let's say I wanted to send a I can send a start condition. Moment I send a start condition, I will get its status as 0x08. So if I receive 0x08, then I know the start condition has been executed. Then at that point I may populate the data condition with the right bit in the control register. So the control register has got the bits STA, STO, SI, and AA. So STA is the start bit, STO is the stop bit, SI is simply a flag which gets set after every control action or every action that you do has been completed. So the SI bit will remain set, and AA is the acknowledge or the not acknowledge bit. Okay, so basically this is all we need. So an action reaction scheme. So we set the action, we start the action by writing to the data register and writing to the control register, and then we get an reaction. The reaction, what reaction is, that is reflected in the status registers. I know this sounds a little confusing right now, and I agree that it is, but it will become more clear as we look at the examples and more in the following pages. Okay, so we are going to look at only two modes here, only the master modes, that is a master transmitter and the master receiver. We are not going to look at the slave mode at this point of time. Okay, now looking at this diagram, we can see here few things very clearly. Okay, that is, whenever I send the start bit, okay, to send the start bit I have to make STA high. Okay, and I set the start bit, automatically the start condition will be put onto the bus, and once the start condition is executed, I will get a status of 0x08, which means the start has been executed. Once the start has been executed, then this is the dark color is master to slave, the light color is from slave to master. Okay, then I populate the data register, and again in the control register I will put that as a 1. I will have to clear the SI bit. So this basically is showing you the entry. The status bits here are showing you the entry into this mode, but as you exit this mode, or as you write something and you have done your action and you want the reaction to occur, at that point you must clear the SI bit. This SI bit has to be cleared, otherwise it will not proceed further. So in that case I write the slave address with the read write bit, I keep it as write, and I will clear the SI bit. Now moment this is done, what will happen is that two things can happen. If the slave exists on the bus, it can ACK me, or if the slave doesn't exist, it can also NACK me. It can give me an ACK or a NACK. So moment this is put and an ACK or a NACK is received, I will again get an interrupt, and in that interrupt I will read the status again to know the reaction, to what my action was. What was the action? SLA plus W, that is write the slave address with the right bit set. So now what is the reaction to that? There can be two reactions, either 18H or 20H. So 18H means the slave acknowledge, 20H means the slave did not acknowledge. Okay, now proceeding further. Once I have this, address is put. Now what I can do is I can just write data to the slave. So remember, what are we talking about? We are talking about the master transmitter mode. Here the master is only writing data to the slave continuously. Okay, so then I put, after I receive this, ACK or NACK. If it's NACK, then it's game over because that slave doesn't exist. If I receive an ACK, then I can again put new data onto this thing, onto the I2C and DAT register, write the new data, and again clear the SI bit. Now after that, again I will get another ACK or NACK, but this time the codes will be different because this ACK or NACK was for the SLA plus W. When it is 28 or 30H, it is ACK or NACK for the data. Now this process can continue until I have put all my data onto the bus. Once I'm done putting all the data, then I would want to either generate ideally I would want to generate a stop bit. So how do I do that? In that case, I will come here, I will keep STA as 0 and STO, I will set the STO bit. And after I do that, I will clear the SI bit. So moment I do that, whatever is the STO, that action will come into effect and it will generate a stop condition. Once the stop condition is generated, again the status will be set to 0xF8. This will indicate to me that my stop condition has been executed successfully. Okay, so after that I have say if you're writing to an EEprom and you write the you want to read data from the EEprom. So typically how would that go? You would first write the address. You would have to write the address of the part, the EEprom part. Then you would have to write the location from where you'd want to read data from the EEprom. So you would have to write 1 or 2 bytes of data. Okay, once that is done, then you would not want to typically, now you would want to change mode to read mode because you would then want to read. So you would want to create a repeat start condition. So for that condition, you would come here. Now, if you remember, we have issued a start condition, but we have not issued a stop condition. At that point, if you issue a start condition again, here you can see STA. This STA bit is set. If I issue a start condition again, then I'm going to be putting out a repeat start condition on the I2C bus. And in this case, I am going to go into master receiver mode instead of master transmitter mode. I am going to change to master receiver mode instead of a master transmitter mode. Okay, so here we know that once we have the stop bit, the status is 0xF8, and at this point when it is 0xF8, we will not get an interrupt. The interrupt is not generated when a stop bit is put onto the I2C bus. So that has to be kept in mind, that there will be no interrupt when the stop condition is generated. Okay, so going further, then we have points where arbitration can take place. So that's that may not happen on a single master. That may not happen on a single master when there is just a single master on the bus. Like you may have your microcontroller and you may have some I2C peripheral ICs, like your I2C peripheral ICs like your RTC or your EEprom, in which case you may not get an arbitration. But then you have, but even if you do, you have the codes for the arbitration. You have 38H for ACK-NACK. You may have, if it's only ACK, you may get 6878B0. These are the codes. So now this is about master transmitter mode. So main thing to keep in mind is that this is an action reaction scheme. You write your data to the I2C and DAT register. You set your control bits in the I2C control register, that is your STA, STO, SI and AA bits, and based on that some action will be generated, and depending on what action is generated, the status is set. So if you read the status registers, like if it's 0x08, you know the start condition has been executed correctly, or if you get 18 or 20H, then you know that whether you have received an ACK or an ACK for an SLA plus W data. So all of these things are pretty easy once you figure out what is exactly happening, because this is quite a unique implementation. This implementation of I2C is quite unique. Now going further, we go to the master receive mode. Again, master receive mode is similar. Now here again, the dark colors, the dark shades are master to slave, the dark shades are master to slave, the lighter shades are slave to master. Now looking here again, once we generate the start bit, we can come here. We get a code 0x08. Okay, so once we get 0x08, then we can write the SLA plus R, because now we want to read the data from the slave. We want to read the data from the EEprom. Let's say we want to read the data. So now we put SLA plus R. After that, we are now in the read mode, and after that, what we will get is we will get a status. We will get a status of 0x40, and we can see here we get 0x40, and that is after you receive a successful ACK. Okay, then after that you come here and now you want to read the data. So for this purpose, you are going to set the data is going to be put automatically, is going to come to you, and an interrupt will be generated. Once that interrupt is generated, you got to keep on clearing the SI bit and set your AA. That is because now the master must acknowledge the slave that it has, okay, I have received the data successfully. The master has received the data. So as long as the master wants to receive the data, he will keep on setting this AA flag, that he will generate an acknowledgement. Now moment the master is satisfied that he has received all the data he wants and wants no more, then he will keep the AA flag 0. That will generate a NAK. That will tell the slave that the master has all the data that it needs and it doesn't need any more data. It is going to stop transmitting, but then it is going to be the responsibility of the master to send the stop signal. So here at this point, after we receive the NAK, what the master must do is master must set the STO bit. Once the master sets this STO bit, then the stop condition will be generated and the status register will hold 0xF8 and no interrupt will be generated. Remember that whenever a stop condition is set, no interrupt is generated. Again, two things can happen after we write the address for the slave. Either the slave acknowledges it or the slave refuses and sends you a NAK, because there is no such slave, or the slave address is wrong or whatever. He may send you a NAK, or the slave doesn't want to acknowledge, he may send you a NAK. So if it sends you a NAK, then what you're going to have to do is you only have the option of sending a stop bit and ending the transaction. So here again, if you have the start bit but you do not send the stop bit, you can again send a repeat start. You can send a repeat start here and then go to the master transmit mode. So from the master transmit mode, you can go to the master receive mode, and from the master receive mode, you can go back to the master transmit mode. Okay. So so much so for this. Then these are just various about slave conditions that we are not going to talk about. Okay, so there's just a few things here. So you may get a status code of 00H. You may get a status code of 00H. So a status code of 00H means a bus error has occurred. So what is a bus error? Basically, a bus error means that whenever you are expecting a start or a stop condition and the I2C master does not receive a start and a stop condition at that point of time, say in between a data packet, let's say the third bit, if it receives a start or a stop condition, then it understands that there is some problem with the bus and it will generate a 00 error. 00 status code. That means that your bus is in error. Now the only way to recover from the bus error is to send a stop bit, to set the stop bit, and once you do that, it will be cleared. The stop bit should be set and the SI should be cleared. So that is the only way to recover from the bus error. Okay, now looking further, here you have a table which lists out all the possible status codes. That is, for start is 0x0x, repeat start is 0x10. Very handy table this, because this shows you all possible status codes. Okay, and then again F8 is bus is released, and like I told you, after you generate a stop condition, you get F8. That means the bus is released and you're done with whatever you have to do. Okay, so then what interesting feature this peripheral also has is called an I2C timeout. So what is an I2C timeout? It is simply a 14-bit counter which is clocked from either FSys or 1/4 of FSys. And this timer, once it times out, it will generate an I2TOF interrupt. It will set this flag and it will generate an interrupt, which was it will vector same to your I2C interrupt. And in that interrupt, you will have because it jumps to that interrupt on this timeout. You have the possibility of knowing that your bus has latched up or it has hung up, and you can recover from there. Now, the only way to clear this timer would be when the SI flag is set. So every time, keep in mind that every time a valid I2C transaction happens, the SI bit is set automatically by hardware. So this timer, if you enable it, will always be cleared. So if your bus and if your I2C network is working fine, this will be always cleared, because automatically after a successful start, stop, or any I2C transaction, the SI bit is always set. The SI bit is always set, and at the end of your interrupt handler, it's your responsibility to clear the bit. So once you clear the bit, the counter starts counting again. So this gives you a very clever mechanism to recover from an I2C latch up. Okay, so now having said that, I just wanted to show you one more thing. This is regarding the baud rate for the I2C setup. So the equation for the baud rate, there is the register called as an I2C clock 8-bit register, which has 8 bits in it, and this register allows you to set the baud rate for the I2C, which is basically fsys divided by 4 into whatever value you have into this register plus 1. So this allows you to set the baud rate for the I2C register, and like they say here, it can go up to 400 kbps, which is good. Now let's look at a code example. This code example unfortunately isn't one provided by Nuvoton. I wrote this from bits and pieces that they provided because it's a more meaningful example. So let's have a look. I'll put a link to this where you can download in the description below, so you could probably use it for your reference. Okay, so the idea here is to take an EEprom whose address is 0x50 and write 5 bytes to it, and then read those 5 bytes. So that's all that this example will do, but this is it can be very useful for showing you how to write to EEproms or on RTC. Okay, so let us just leave the interrupt handler for now. So we write the I2C initialize. Here we can see I2C open. We put the fsys, the clock, and we put the speed that we want the I2C module to run at, and this routine will do all the rest. We enable the I2C timeout. We enable the 14-bit timer on this, and we enable the interrupt. Now whenever we do the reset of the I2C bus, it is exactly the same. Reverse of this, open will be closed, enable will be disabled, again the enable it will be disabled. We disable all of that and then re-enable everything. So everything is initialized. Now here you can see we start the main with 1.3 GPIO being made into push-pull mode, and then we have 2.4, which is the SDA pin. We start with this SDA pin being made open drain. Like I told you, for I2C to function, both the SCL and SDA have to be open drain. So I make this open drain, and I make P2.5, which is SCL, also open drain. Now here I have both of these pins made as open drain. I start the I2C bus. Now here I have the EEprom slave address, which is 50H. I showed you here. So this is 50H. So I write this address to this U8 device address variable, and I have about 7 variables here, an array of U8 data. So how do I populate them? Now my idea is to write 1, 2, 3, 4, and let's put this as 5 to the EEprom, the 5 bytes of data to the EEprom. So I'm going to write it at location 0x1000 at 1000H. I'm going to write this at 1000H. At 1000H, what am I going to write? 1. At 1001, I'm going to write 2, 3, 4, and at 1004, I'm going to write 5. So then I need to populate these variables with the total number of bytes. So this is what is the total number of bytes? These are 7, 0 to 6. This total number of bytes is 7. Then this is the running counter, which I will keep right now as 0. You will find most of these code is commented. So you will see that I2C TX complete, whether I want a complete transfer or I just want a read or a write That's important. So here I don't want the complete transfer, because I'm not going to read something from the EEprom. Complete transfer will be useful only when I'm reading something. Here I just want to write, so I'm not going to use the complete transfer option. Okay, I'm going to keep that as 0. Then I'm going to see read flag, whether I want to read or I want to write data. So I'm going to keep the read flag as 0. I'm going to keep the end flag as 0, because end flag will just indicate that the transaction is completed. And I'm going to keep the error flag as 0. And I am going to set the STA. I told you. So STA, moment I set the STA, what am I doing is that I am going to start the transaction. I'm setting the start bit. Okay, so we are here. So I have set the start bit, and now I should expect a 0x08. Now looking back at the interrupt, once I go back to the interrupt, okay, so this is my I2C interrupt, and I will get 0x08, which is the start, and 0x10 is repeat start. Okay, so I will clear the start bit here, and I will see whether this is read only flag is equal to 1. Yeah, but my read flag is 0, because I'm only just wanting to I just want to write the data right now to the EEprom. So this is 0. So I'm going to come here and I'm going to give the device address, shift it left by 1, because the least significant bit is the read write bit in the address. So you can see here the least significant bit here is the read write bit for the address. So I do that, and once that is done, I will execute a write transaction. Now once the write transaction is executed, now we'll try to compare this with the diagram. Okay, it will make it more clear. So now we are at 0x80, that is we are here, and I have issued this start command. I have put this, okay, and once I do this and I clear the SI bit, the SI bit is cleared at the end. I clear the SI bit. That means now this transaction is going to, whatever I have put into the data register is going to be put out. So moment the data register is being put out, then I will have two options. I will again get an interrupt where the status code will be either 18 or 20. Either 18 or 20 will indicate whether the address was ACT or NACT. Let's have a look. So you can see here, if it was 18, means SLA plus W has been transmitted and ACK has been received, means the slave acknowledged the address. Okay, if the slave acknowledged the address, then I must put new address. I must put the next data into the location. This will be the address data. I want to write at 1008, so this will be the MSB of the 1000. I will have to put that, start putting that into the I2C 0 DAT register. So that's here. Now once that executes successfully, again I will get two codes, either 28 or 30. So when I get 28 or 30, then what's going to happen is that I will come here. By the way, if the slave nacked me, then what would I do? I would send a stop bit. I would set the error flag and I would set the end flag, because that's the end. The slave has nacked me at the address point. Address, when I just simply put in the address, that means there was no such slave. So we should not be proceeding further. So I just stop, release the bus, and I'm out of here. Then if I get 28, that means the address was acknowledged and my first data which was put in was also acknowledged. This means that data has been transmitted and acted by the receiver. The data has been transmitted and acted by the receiver. Okay, so now if this was the case, then I will come to 28. Then what I'm going to do is I'm going to keep on putting all the data that I need. And once my data is completed, whatever data I have to write to the slave, including the address and then the data bits that I need, once those are all gone, then my data length is going to equal to tx limit, and I'm going to come here. Now here what's going to happen is that I'm going to see whether I want tx complete. No, I don't want tx complete, so I'm simply going to send the stop bit. Okay, and I am going to I'm going to set the end flag and the error flag, so my error flag is going to be clear. So now this point of time I have finished writing to the EEprom. All the data that was meant for the EEprom is going to be written, and here I'm waiting while I2C end flag is equal to 0. I'm going to wait. So I'm going to wait for all the transaction to complete. Once that is done, I'm going to check whether if it's F8 means okay, everything was completed successfully, I'm done here, or there was an error. So if it was F8, or an error, means that particular transaction is done, I'm going to simply clear the flags and I'm going to reset the I2C peripheral. Although I'm not sure that at this point of time whether this would be necessary for the code F8, because F8 would successfully mean that the bus has been released by the I2C peripheral. Okay. Now moving further. Now the next part is where I would want to read the data from the EEprom. Now I have written, I want to read the data. So how would I read the data from the EEprom? To read the data from the EEprom, first I would need to write its address and then issue a repeat start. And once I issue that repeat start, then I can read the 5 bytes of data. So okay, let's see how that is done. That means I would need to do a complete transaction, because I would have to do a write and then I would have to do a read. So if it's only a read or only a write, then that's a partial transaction. But I want to do a write of the address, write the address of the EEprom from where I want to read the data. Let's say 1000H is where the data is stored. So I want to put the 1000H, I want to write 1000H into the EEprom, so that in the EEprom its location counter is reset to 1000H, and then I start reading data from that location. Okay, so let's see how it's done. So this is a complete transaction. So I put, again like previous, I populate the address because I want to read data from 1000H. I put the data limit as 2 because only there are 2 bytes, and I put the limit as 5 because I want to read 5 bytes of data. At this point we are going to put the TX complete as 1, yes, because the whole transaction must be completed, and I am going to proceed and I'm going to set the start bit. So then what happens? Everything happens the same way till all of this will happen, just like previous, but I am going to come here. Now at this point, when my 2 bytes are finished, that is I have written the address, I have come to TX complete. Now TX complete is 1. We have issued the start condition, but at this point we have yet not issued the stop condition, but we are setting the start flag again. So it's going to generate a repeat start. Okay, and I am going to put my read flag as 1 because now I want to read the data. I don't want to write the data, I want to read the data, and I will set u length as 0. So what's going to happen now? Okay, so where are we right now? We are right here in the transmitter mode. We have generated this repeat start, so we should expect the status to be 10H, and we are going to go to master MR mode, master receiver mode. So we come here, instead of 0x08 we are going to come to this mode with 0x10 because we've generated a repeat start. Okay, let's have a look. So we come here with 0x10, we have generated a repeat start. Now because we have generated a repeat start and we are in this mode, now we are going to because my read flag is set, I am going to generate a read condition on the I2C bus. I'm going to generate a read condition on the I2C bus. Yes. Now once the read condition is done, I am going to come here. This is going to be the code for the read condition. So what's going to happen? Let's look at the flow diagram again. I'm going to get a status code of either 40H or 48H based on whether I receive an ACK or a NACK. Yes, people, that's what's going to happen. So if I get 40H, then I know that I have received an ACK. So what happens if I receive an ACK? When I receive an ACK, I simply put data into the I2C DAT register. Yes, and then that data should be put. Oh, I'm sorry, we are reading. So what I'm going to do is once I receive an ACK, I am simply going to clear the SI bus and I am going to set the acknowledge, because this acknowledges for the byte that's going to come in. Now you have to remember that we have not yet received, we have just received the ACK and the bus is held steady at that point of time. Now if I clear the SI bit, I will start receiving the data. The clocks will start moving out. I will start receiving the data from the slave. Now, moment I receive the data from the slave, I need to do 2 things. Either that data has to be ACKed or has to be NACKed. If it is the last byte that I want, then I have to NACK it. If it is not the last byte that I want, then I want to ACK it. So I'm going to have to set the ACK or the NACK before that data comes in. That is, your status is 40H. You are here. At that point of time, I need to set this AA flag. Okay, so I'm going to generate an ACK. Let's look at it in code. So what I do is 40H, I set the AA bit. So I'm going to be able to acknowledge that data. So now as that data starts moving in, what happens? A data with an ACK comes in because you have put in an ACK. So at the end of this, you are going to get an interrupt with the status going to be 50H. Yes, people, status is going to be 50H. So we come here. When the status is 50H, we recover that data. Whatever was in the data register, we put it into our buffer because we need that data. That is the data we want to read from the EEprom. Now we will again compare the incoming data with the limit that we have set. So we need 5 bytes of data. So basically we acknowledge byte 0, byte 1, byte 2, byte 3. But for the byte 4, that is the fifth byte of data, we are going to keep this AA flag cleared, which is going to send a NAC. That's going to inform the slave that look, the master is now done, it has read all that it was to read and doesn't want any more data. So here we are not going to read any more data after this. So once we put in the NAC, what happens? So if we put in an ACK, the cycle just repeats, it goes to 50. But one moment we put in a NAC, it comes to 58H. The status will be 58H at the end of the byte which was NAC'd. So once we receive 58H, then we must put in the stop condition and release the bus. So we are going to come here and we are going to put the STO bit as 1. So at 58H is our last byte, which was we received as we had NAC'd previously. We have got the data for the byte that we NAC'd, and that's the last byte that we need. So we put that into our buffer and we set the stop bit. We set the end flag. We put the clear flag as 0 because everything we did now we're done with it. We've got everything we wanted and we proceed. Now remember I told you that we have a special case of 00. That means that there is a bus error. Whenever there is a bus error, you need to again set the stop flag for the bus error to clear. Okay, and set the end flag and we set the error flag. Okay, so in this case there is no error because obviously everything ended just as we wanted to, but we only set the end flag. So once this is done, we come here and we will proceed. Code will move on from here because it was waiting. Now this becomes 1, so code comes down and we have received our data in the buffer. Again, we just clear all the variables and reset the I2C. So that's about it for the I2C peripheral. I think it's quite easy, quite an innovative approach for the I2C in this module. So I hope you enjoyed it. Thank you.